Here's the first definition. A function, capital F, is an antiderivative of f on an interval I if f prime of x is equal to lowercase f of x for all x in I.
Hey, Professor.
Yes.
Hey, your connection is fluctuating.
Am I going in and out?
Barely, but it's more of the for the picture. Like for instance, this is clear now, but it starts to distort, so it's kind of hard to see like what you're writing sometimes because of the fluctuation of your connection.
I think it's when I put my hand on here. It's
Well, the
autofocus
hand
is
comes
changing.
out pretty good.
Let me see. Is it
um,
changing?
yeah, yeah. Actually, it kind of is.
Yeah. Um, yeah, I don't know if I can fix that part, but we'll
That's
see.
fine.
We'll see. Okay. Let's see here. So far, function f, capital F, is an antiderivative of lowercase f on an interval I if f prime equals f. So that's how we're going to define the antiderivative. And just a quick example. If lowercase f is equal to 3x squared, then capital F would be equal to x cubed, right? Since the derivative of capital F, which can be written this way, right? d dx. Guys, I'm assuming you're all experts at derivatives at this point. Which can be written, of course, as derivative with respect to x of x cubed, which would give us 3x squared, right? So that's the definition that's being applied here. That's what this is saying, okay? This guy is the antiderivative because it's going in reverse from the derivative.
So where did the three go then?
The 3,
Yeah, from the antiderivative, it's 3x squared, and then for the actual derivative, it's x cubed. So does the 2 and the 3 flip?
no, this is the antiderivative here.
Oh, that is. Oh, okay. I thought the bottom was the antiderivative.
Yeah, so if you take the derivative of the anti, you get here. So
Okay.
basically, if I go in reverse from here to there, would be antiderivative.
Okay. So quick question here. So
Mm-hmm.
if I have a if I have a 4x squared with the antiderivative be x to the fourth?
4x squared, it would be x cubed.
I'm sorry. So it's 4x cubed with the antiderivative would be x to the fourth?
So you said if you started at 4x squared, you're asking what the antiderivative is?
Yes.
Oh, that would be, let's see here, 4/3 x cubed.
4/3 x cubed. Oh, okay. Okay. I think I get it. So anything's going to be over the 3. So if it would be like 12x cubed, it'll be 12 over 3x cubed.
Yeah, so I'll show you the general rule in a moment, but yeah, I think you're getting the idea.
Okay. Appreciate it. Thanks.
Mm-hmm. There, you got it, man. Let's see here. Although there's something that we need to note. So note there are other possible functions f1 of x equal to x cubed plus 1, f2 of x equal to x cubed minus 5. You see how these would all technically work, right, as the antiderivative?
Not really.
What would
I'm
happen if you
thinking
took the derivative of each of these? You would still get this, wouldn't you?
f2, f1, f2, f3, x3 minus 5, 1 plus pi. So would it be pi over 3 to this x squared for
What is
f3?
the derivative of a constant?
0.
Yeah, so the constants have no effect on the answer. It's still going to be this right here. But technically, there is multiple solutions to this antiderivative. It doesn't have to be this guy, right? It could be either of these three. Technically, there's an infinite number of solutions.
Okay.
So since the derivative of any constant is 0, and f1 prime is equal to f2 prime is equal to f3 prime, which is 3x squared, right? So this idea comes in, we're not going to go too deep into this, but this whole idea right here, multiple functions, becomes important in differential equations. And the initial condition of a physical problem, like if you're in a real world problem, giving an initial temperature, an initial position, initial velocity, whatever we're talking about, that will determine what the function will look like, even though they're similar, right? So there's like a starting point. So that will tell you which one is the one you want. But we'll do a little bit of that. We'll touch on it, but we're not going to go too in depth. The depth is for differential equations, which is later, assuming you're going that far. Okay. Let's move on here. So another theorem here. So if f is an antiderivative of lowercase f, let me zoom out here. Yeah. On an interval I, then capital G is an antiderivative of lowercase f, lowercase f on I. There we go. But it's only true if and only if G, capital G, is of the form G of x equal to capital F plus some constant C for all x in I, where C is a constant. Okay. Let's see here. So let me give you an example. Let's see what the heck that's saying, right? Because it's kind of wordy. So basically what we're saying is there's a general solution called G for a differential equation. So we'll do some basic differential stuff here. Find the general solution of the differential equation y prime equal to 2. So basically, what is a function that has this derivative? That's what they're asking. What function has this derivative? What do you guys think?
2x.
Yeah, 2x, right? So y equal 2x is a specific solution using this theorem, or this idea. What would be the general solution? Might still be 2x, but we have a possible constant of where c is any number, right? You see what I'm saying? So this is the general solution. Does that make sense?
Yes.
Yes.
And do you remember, I assume you did a little bit of antiderivative at the end of Cal 1, right?
Yes.
Do you remember how you would integrate or do the anti and you'd end up with a c?
Yes.
Yeah, this is why it's important. It's because the solution is a general solution. C can be anything, and C will be determined by real life problems or some sort of initial condition, initial time, etc.
Okay.
So we have to put it there. All right, let's move on here. Let's talk about some notation, just in case you guys forgot. You guys cool if I turn the page, or I'll scan to see you later as well, but if you want me to wait, I can. You guys cool then?
Yes, sir.
Okay. So notations for antiderivative. Sorry, I wrote that pretty messy. Notation for antiderivative. Since dy dx is equal to f of x, then dy is equal to f of x dx, right? Technically, I could separate this and put the dx over here with multiplication, correct?
Yes.
All right. The operation of finding all solutions of this equation is called antidifferentiation. Antidifferentiation. Which we later start to call indefinite integral. All right. and is denoted by an integral sign looks like that whole S thing. Okay. General solution looks like this, or is denoted this way. Y is equal to the integral of f of x dx, which is equal to capital F of x plus c. So basically you integrate both sides of this to solve for the original function y. That's what the integral can do for you, giving you the antiderivative, or in other words, the general solution. Okay, so that's like the whole, like a quick recap on this theory behind the integral stuff, which they already talked about at the end of Cal 1, but I want to touch on it a little bit before we start getting into solving problems. Okay, let's go over the basic rules. You guys have any questions so far? You guys doing okay?
Yes, sir.
Okay. Ready? So the integral of a derivative cancel out, giving you just that function, plus c. If you do it the other way, you take a derivative of an integral, then you're left with just that function, which is coming from the fundamental theorem of calculus. So they're basically inverses of each other. Derivative and antiderivative are inverses. Okay. Some more theorems. Some properties of the integral is you can factor out constants outside the symbol. So if you have some number times a function, some number a, plus some number b times another function, then you can separate it this way. See what I mean? So you can separate sums and integrate separately. You can pull out constants out here and then integrate. Where a and b are real numbers. Okay. All right, so let's do some examples and mention the power rule. Integral of a power function or polynomial will simply be n plus 1 over n plus 1 plus c. That's how you reverse the derivative. Okay. So for example, pen's dying. Let's see here. The integral of 2x dx this pen has any ink in it. Would simply be yeah, I forgot to buy new pens today. It's my bad. That's going to be 2x. Let's switch out something else. I'm going to use these light colors. Okay. Does this work? Yes. I don't like how light that is, but oh well. All right, so integral of 2x dx would simply be 2x to the first power plus 1 over 1 plus 1. So that would end up being 2x squared over 2 plus c, giving us x squared plus c, right? So most of the questions that start out will be just simple power rules. Okay. Alrighty, another one.
Quick question.
Mhm.
So x squared plus the constant, that's the answer? That's our answer?
Yeah, that would be the answer.
Understood. Thank you.
Okay, so maybe there's just something on the paper. All right. Let's check this one out. 1 over x cubed dx. So you need to first set up the question because the power rule can't be applied directly. So you have to use your algebra to rewrite the question into x to the negative 3. And then power rule says you add 1 and then divide by that result. So negative 3 plus 1 over negative 3 plus 1 will be your answer. So that is simply x to the negative 2 over negative 2, which is this guy. So there'll be questions where you kind of have to set it up first and then do your integration. So the power rule can't be applied unless it's written in this form. You see what I mean? You can't do it here.
Question.
Mhm.
So I get the first step. If you went from derivative of 1 over x cubed derivative of x, and then turns into, because you flips it from x to negative 3 derivative of x. But why was it plus? Why does it come to the third step, which is x raised to the negative 3 plus 1, and then negative 3 plus 1's in the bottom?
Yeah, so
How does that form?
that's the power rule right here. So whenever you have any variable, when you're integrating with respect to that variable, you simply add 1 and then divide by that result. That's it, every single time.
Okay.
So since we had a negative 3, it was negative 3 plus 1, negative 3 plus 1. And that's your antiderivative.
Okay. Thanks.
Let's do another one where you're going to have to set it up. Integral of square root of x dx. So how can I rewrite that square root?
X 1/2.
Yeah, so rewrite it as 1/2 and then do your rule, right? So that would be x to the 1/2 plus 1 over 1/2 plus 1. That's my answer. Simplify this, that will give us x to the 3/2 over 3/2, which is simply, let's forget my c there, which is simply 2/3 x 3/2, right? Do you have any questions on the algebra or power rule? You guys okay then?
For me, yes.
All right. Well, let's go review our trig. What's the antiderivative of sine? Yeah, it helps to know the derivatives, right?
Mm-hmm.
So we'll just write them down over here somewhere. What's the derivative of sine?
Cosine.
Okay. What's the derivative of cosine?
Negative sine.
Okay. So I have a sine, right? So taking the antiderivative of sine would take me to, well, negative sine would take me to cosine, right? Going the other direction.
Mm-hmm.
But I don't have a negative. So what do you expect the answer to be?
A negative cosine.
Yeah, just negative cosine. Right, so if it was the integral of negative sine, it would simply be cosine. Right? Does that make sense? So for these, you kind of have to know the antiderivative. There's no, it's not, this is not a power rule kind of question. You got to go backwards. Alrighty. What about this one? This requires some memory too.
Is it x raised to the -1 plus 3? No.
Well,
I think this is just ln x, right?
yeah, so we got to remember the derivative of ln.
Yeah, Ellen, that's right.
It's going to be this guy. So when you see an x on the bottom with no power, right, it's going to be ln. This 3 is in the way. So remember how we have the rule that says you can pull out constants. Right? So that would simply be 3 ln x plus c. But anyway, those are all questions that I think you've already done before. So I want to make sure we discussed it a little bit. Okay.
Do you have to put like the absolute value or no?
It depends how they define x. Since I did not define it, yes.
Okay.
If they
If,
tell you that x is positive, then you don't have to.
Thank you.
Sorry about that.
No, that's fine.
I get to ask a question.
Yeah. What's your question?
I know you said if x does not have a power, but if it did have a power, would it still be ln x?
You mean like if it was a square?
Like it was x squared cubed to the 4th, 5th.
Yeah, you would use the power rule like we did up here, this first one.
Understood. Thank you.
So the ln is only when you have power of 1, and it's on the bottom.
Okay. Thank you.
Alrighty. Let's see here. We're still good. Right, I'm gonna turn the page. That's cool. Let's do some more complicated questions. So integral of, let's say, 3x to the 4th minus 5x squared plus x dx. So how would you approach this?
Just split it into 3 integrals.
Yeah, we gotta split it, right? So that'd be integral of 3x4 dx minus integral of 5x squared dx plus x dx. Okay. These are all going to be power rules, right?
Yes.
So what is this first answer going to be?
Um,
3/5 x to the 5th.
Yeah. 3/5 x to the 5th. What about this guy?
5/3, right? X
Yeah.
to x to the
5.
third.
Yep. And the last one.
1/2.
Yeah. X squared over 2 or 1/2 x squared.
Okay.
And I'm sure some of you might be wondering, well, what about the c, right? Technically, there is a c each time. C1, C2, C3. But you can always redefine the c. I can say, you know what, let C1 plus C2 plus C3 equals c, because it's still some constant, so you don't have to worry about it. C is just some number. If I add a bunch of numbers, it's still some number. Who cares? That's why I just tack it on at the end and not worry about it.
Oh, okay. But like the actual well, not the actual, but the actual way is supposed to be 3x to the 5th plus c minus 5/3 x cubed plus c. Seen everyone?
They would be different c's technically.
So it's C1, C2, C3, C raised to the first, third. Is that
Yeah,
correct? Okay.
but since it doesn't really matter and we don't have a initial condition, and we can redefine all of those c's to be a single c, I'd say
Understood.
just tack this on at the end. Okay, let's see here. So sometimes you gotta get creative as to how to integrate. See how here all we had to do is separate it and it wasn't too bad, right? Sometimes you gotta think about it. Like, what can I do here? Integral. Let's do this weird guy here. X plus 1 over square root x. How would you integrate this?
First, I would go x plus 1 over x to the second power, or x plus 1 times x to the second power.
X plus 1 times.
Or it could
Didn't
be.
you? So go ahead, buddy. Sorry.
Oh, I'm sorry. I was just gonna say, could you subtract the denominator from the numerator, or not like subtract it, but like write it like in standard form? I can't really explain it well, but
I think I know what you're saying. You want to divide the denominator, right?
yeah,
You can separate this fraction technically,
I meant separate the fraction.
and then divide it out. So now we can pretty much do it. What is this guy going to reduce to? What is x divided by square root x?
1?
Hmm,
Or I'm sorry, is it 1/3 like we said last time or earlier, something like that?
well, let's look at it. That's the first power on the top and a 1/2 power on the bottom, right? So when you divide them, what do you get?
Just 1/2.
Yeah, it's going to be x 1/2 dx. All right, and then this one, you have to bring it up, right? This would be negative half dx. Does that make sense? How you set them up? Because at first glance, it was like, how the hell do I do this, right? But once you do this, it's just basic power rule. No big deal. So this will be, add 1, that'd be 3/2. So 2/3 x 3/2. We did that before. Add 1, that'd be a positive half. So that would be, let me show the step here. Plus 1, negative half, plus 1. right? So then we're done. It would be 2, right? Because it would be 1/2 on the bottom divided by 1/2 turns into 8/2. I skipped an algebra step there. Is that okay? It skips 2 steps technically. Is there any questions on this problem?
No, sir.
All right. Okay, let's see here. Can do 1 or 2 more and we'll take a break. All right, integral of sine x over cosine squared x dx. How do you approach this?
Do we have to take the derivative of sine x? So it would be what, negative cosine x on the top?
Well, you can't just integrate the top separately.
So we have to separate the bottom first, and then the top?
There is no rule that lets you separate products. You can only separate sums and differences. So you got to attack it all together. So
Okay.
what you got to come up with an idea to rewrite the question that makes it an easy integral that you already know.
Can we multiply them?
What do you mean?
Like it'll be integral sine cosine x and integral cosine squared. No, wait, sine squared x, right? Times.
You want to multiply sine on the top and bottom, or is that what you're saying, or what do you mean?
I was thinking of doing what we did above here, is where you take the integral of sine x and then flip it, right? Could we flip it?
No, we can't flip it.
Okay.
Yeah, it's a little tricky. Let's think about this. So do you remember back in pre-cal doing the identities and proofs and all that stuff?
No,
It was a while ago, right?
forever ago.
But you do remember that you did that at some point, I hope.
Yeah, sure.
Okay. So basically, you gotta get creative and rewrite the question using your trig identities. So these can be difficult if you don't remember your trig stuff, because trig comes back in Cal 2. You don't really see it much in Cal 1, but in Cal 2 you do. So I rewrote the question. Do you agree that this is the same?
Yes.
What is 1 over cosine?
Isn't it just cosine?
No. Well,
Back, we're talking about pre-cal, right? What is the reciprocal of cosine?
secant.
Secant, right? What is sine over cosine?
Tangent.
Tangent. So now we can rewrite this as secant tangent. Right? Do you agree?
Mm-hmm.
What is the antiderivative of secant tangent?
I don't know.
Just secant, right?
Yeah, it's going to be secant. What's the derivative of secant? This is Cal 1 now, right? What is derivative of secant? Right, it's secant tan, correct? You remember? So the integral of secant tan should be secant, since this is the derivative of that.
Mm.
So you have to remember your trig derivatives when you're dealing with sine and cosine, okay? Or secant, cotangent, etc. All right. You guys have any questions on this problem? do one last example, and then we'll take a break because then that's a lot of stuff. Okay, so this is called finding a particular solution. The question is basically find the general solution of f prime of x equal to e to the x. And then find the particular solution that satisfies this initial condition. So I'm actually going to give you initial condition this time, which means you're going to solve for C. Okay. So general solution we've done before. So we're going to do that already, right? And we're all comfortable with derivatives of the exponential function, right? What's the derivative of e to the x?
E to the x, e to the x.
Yeah, so since that's going to happen, we know that the general solution would be this, right? General solution is this guy here. So all you got to do is integrate it. And since we know the derivatives are the same no matter what, you just go in reverse, right? Now the particular though. So use this initial condition, f of 0 equals to 3, to find C. So just plug it in. So f of 0 equals e to the 0 plus C, which is equal to 3. So that means that 1 plus C is equal to 3. So C is equal to 2, right? Does that make sense?
Yes.
Once you have C, then you have found a particular solution, right? So that means the particular is f of x equal to e to the x plus 2. So this is a specific solution given some initial condition. So the homework's going to have you, they'll start off just doing basic antiderivatives, power rules, or maybe some weird types of power rules where you got to set it up. Then you'll have some sine cosine stuff in there, and then you'll have some differential equation stuff where you need to solve for C. So that's pretty much the first section of the homework. All right, so we'll take a break here. It's 9:04. Let's come back at about 9:10 or so. Yeah, maybe let's say 9:15. We'll stop for a sec. Okay, you guys familiar with the notation? If not, we're going over it again. All Alrighty, and can also be used inside of a function. If I equals 1 to n, f of I means you would start at 1 and go all the way down till n. Okay. I is the index. A sub I, or f of I, are the ith term. One, the number 1 at the bottom, is the lower bound, but it can vary. It's not always 1. N is the upper bound. So for example, let's do a couple examples to refresh our memory. The sum from I equals 1 all the way till 5 of I plus 1. So that means you would cycle from 1 all the way till, actually let's put 0, I guess. So cycle from 0 to 5. So that would be 0 plus 1 plus 1 plus 1 plus 2 plus 1 plus 3 all the way till 5. You see what I'm saying? So this I is cycling from 0, 1, 2, 3, 4, 5. Okay, that's what this does. But since it's a summation, you got to add them up. So this would be 1, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, all the way till the last term. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, what's that going to be? 21, is that right? Yeah, that's right. Does the notation make sense?
So is it going to get incremented by 1 every time, or no?
The index, yes. So this is the starting point. Whatever starting point, all the way to the end point would be incremented by 1.
Okay.
But only the index is being incremented. The rest could be, there could be all kinds of stuff in here, right? Like for example, it could be, I don't know, j equals 0 to 4 or 3 of j squared. So that would be 0 squared plus 1 squared plus 2 squared plus 3 squared. So this is increments of 1, but the operation is whatever's in here, right?
Okay.
Be 0 plus 1 plus 4 plus 9. What is that going to be? 5.
14.
Yeah, that's right. 14. Okay. Is there any questions about the notation? Does it make sense?
Yes.
Yes, sir.
All right, so let's go over some properties of summations.
Hey, Professor, you may need to move it up by any chance. There we go.
About that?
Awesome. Yes, sir.
Okay. So here's one property. See how this is I and N? this K is not an I or an N, so you can just pull out in front. Doesn't do anything for you. So this would be equal to K times the summation of I equal 1 to N. So basically you can pull out the K. Okay, another property. They're very similar to the integral properties because the integral is actually created and defined from summations. So we're going to have AI plus or minus BI, which means you can separate it into a sum of AI plus or minus a sum of BI. That looks kind of ugly, but you see what I'm saying? You can just put the sum on each one separately. There we go. All right, so those are two properties we have. I'll give you the formulas you're going to need for the homework. So if you have a sum from I equals 1 to N of C, that would simply, the answer would simply be just C times N. Okay. Now, if you have I equals 1 all the way till N of the just I, the formula will be just N times N plus 1 over 2. I might not have space for this. Thought I would. No, well. You have the summation of I squared, that would become N times N plus 1 times 2N plus 1 over 6. Now, if you have the summation of I cubed, that would become N squared times N plus 1 squared over 4. I guess I kind of jammed them in there, but you can read that, right?
It's just a connection. It makes it distorted.
Let's see here. Is that better?
Kind of. Yeah. 1 second. Let it. Okay. There we go. Yeah. N plus 1 raised to the second. Okay. Cool.
Okay, so there's one for constant, first power, second power, third power. Alrighty.
Is there a way like we could kind of like Pascal's triangle, like you can figure out certain power rules? Is there the same way with like the eyes in connection with those, whatever they equal to?
I mean, there is a way to derive them, but it does take some work. But I wouldn't suggest deriving every single time. And there's only, I think there's only a few anyway. I don't think it keeps going to n.
So it won't go up to like I to the fourth or anything like that, right?
No, you'll have to try to get creative and try to like separate it.
Okay, gotcha.
So you can use like the square or the cube or something.
Gotcha, gotcha.
Let's do let me find an example for you. So these are the important summation formulas you're going to need. Okay. It's an example. So the summation of I equals 1 to n of I plus 1 over n squared. So you got to figure out, okay, well, how do I approach this, right? You got to use all our properties to figure this out. Since that n is not associated with the I, you can pull it out in front. It's the first thing you can do. So this is really 1 over n squared, which we will deal with later, not right now. Like this. Now, we know we can separate these, right? Into two different sums. So I can do the I plus the sum of the 1. Excuse me. So what is this, the formula for just the first power? Right, this guy will be simply n times n plus 1 over 2. So this is n times n plus 1 over 2, and this guy is simply n, right? Using our formulas. So then just multiply the 1 over n squared, and we're pretty much done. Let's see here. We can also add these up, right? This is the same as n times n plus 1 plus 2n over 2, which will then become, let's see here, n squared plus n plus 2n over n squared. Forgot my 2. Right? But at this point, we're just doing algebra. It doesn't really matter. But do you see the application of the formulas?
Yes.
Okay. Then we'll leave it right here. So finally, it would end up as n plus 3 over 2n, right? So you have a bunch of problems where you have to do that. You have to get creative and try to simplify it, or they give you a large number, and you got to try to make it easy. Like, for example, they might say, let I go from 1 to 20,000. Yeah, okay, well, I'm not going to add that 20,000 times, right? So you have to use your formulas to help you out. That'll be pretty much the majority of the next homework. You guys have any questions about that? Is that straightforward?
Yes.
Sure.
All right. Let's see here. So the next homework would be using the integral to find area. Let me see, or look at my schedule. If yeah, I think we should do it. That way we'll have less on Monday, on Tuesday. We're gonna have 1, 2. Hold on a second. I think we're